Hi everyone, great to see you all. I'm going to be talking a lot about, I've changed the title slightly, but I'm going to be talking a lot about sort of thinking about bringing machine learning into what I think about the sciences and engineering. Machine learning obviously has been very successful in language, speech, things of this nature, right, and also ChatGPT type models. But when we come to physics-based models, one of our first goals in physics-based models is often to extrapolate, build new things that we don't have data for. So how do we start essentially using all of our physics knowledge inside of machine learning tools? I changed the title here to this idea of sensing because actually if you ask me what the miracle is not machine learning. The miracle is sensing technologies. If you look what we can do with sensors now, especially in the sciences, it is actually, it's just absolutely staggering. Whole brain imaging of mice while they're doing activities where you can record from 2,000 neurons simultaneously. If you told somebody 20 years that we could do this, I think they would have not believed you, for sure. And then those are the data streams that are allowing us to start to think about how we might do physics sort of in this next generation. So this is kind of where I want to start with. Everything starts with a sensor, okay? And so I want to start thinking about this as a foundational piece of, I want to think about something I'm measuring. That's X, that's a state space. Could be my fluid flow, could be my brain activity. And I have some measurements, S, of that system. Now what's interesting is we live in a world of a sim to real gap. It's very easy for us to construct simulations of many systems, and we can have access to all the variables. But in a lot of very complex systems that we're really trying to understand, we have limited access to sensor streams on them. Okay? So often S, there's P measurements of a system. So maybe one way to show you this is through a picture. So here, for instance, is isotropic turbulence, and I have some sensors in there by the dots. But really the full state space is that whole entire thing. And what I'm trying to do is, can I measure from those dots, point measurements, reconstruct the full state space? That's kind of the idea. So the idea here is really to think about constructing a map. The map from the sensors to that full state space. Okay? Now this will lead us down the path of much bigger things. I'm framing it initially as a sensor problem. But really what I want to do is I want to learn physics. And I want to build reduced models for these very complex systems. All right, so here's the optimization then we have to solve. The optimization is pretty simple to frame, which is try to learn this map F that measures sensors to full state space. Okay? This is a very standard sensor problem formulation. It's a simple math idea in many ways, and there's many ways to do this. And you can write it down as an optimization problem. Okay? And by the way, this is a little busy slide, but the easiest way to do this is with a linear map from the measurements to the sensors. And the way you could do this is through what's called the singular value decomposition. So I see a lot of younger people here. So if you haven't learned about the singular value decomposition, right after my talk, go learn about it. It's the most important linear algebra trick in the entire world. I'm not lying. That's totally true. So the singular value decomposition is a way to look for low-rank subspaces, feature spaces, and I want you to build models. This is what we originally did with trying to recognize faces. It was called principal component analysis. Okay? It is the oldest trick in the book. And this is how you would do it in this linear map. If you learn that feature space, all you have to do is take essentially measurements and project onto those feature spaces, and you have a projection back to the full state space. And with that comes this idea that I have to find good measurement locations and so forth. There's a lot you can learn from these very simple linear maps. But I don't want just to think about my system as sort of this static thing. I'm thinking about measuring systems like weather, climate, fluid flows, electrodynamics, things that are changing, in fact, in time, spatial-temporal systems. So I'm thinking of a much broader thing that I actually want to do, which is I want to go from measurements, and let's call these measurements now Y. I have a set of measurements out of the system, and I'm going to tell you what I'm going to try to do with it. First, I'm going to try to figure out from my measurements, can I learn what the right variables are, or the right state space? Okay? I might not know what they are. I might know what they are. But often I'm going to say, I'm measuring whatever I can. If I have a thermometer, I'm going to measure temperature. But what I really want to learn is what are the right variables characterizing the system? That's X, my state space. So I have to not only learn what X is, I have to learn how to map what I'm measuring through H to that. And then I want to learn the dynamics of that variable. Okay? Notice, I'm giving you one set of measurements, and you're going to have to learn 3 things. This is an impossible task. Okay? In math, we call this ill-posed, right? You can't solve it unless you start to impose restrictions on this problem. That's called regularization if you're in machine learning. Okay? And so what are the regularizations we want to make? Well, first, I want to talk about this in a very concrete way. And also, because I have 3 things to learn, there's a little bit of possibilities here for me to learn different things, maybe not uniquely. And in fact, this gives us back to 1960. Now, Albert Einstein certainly highlighted this for the first time in a very rigorous way, which is the idea of it doesn't really matter what coordinate system you measure in. When you measure that system, you're measuring the same phenomena. So in other words, this idea of equations and coordinates come in pairs. Okay? And what do I mean by equation and coordinates? So I want to give you a very specific example, and then we'll build from there. And the very specific example is this. This is the night sky. And what you're looking at here in the foreground is the retrograde motion of Mars, and this is the retrograde motion of Saturn. This was physics. Before we have written records, we know that humans were tracking this. Right? So this is a really old problem, and what people wanted to understand was the motion of the planets and making predictions about their pathways. In fact, so interesting were they, right, that we gave them the name of the Greek gods. 6 of them. We didn't know about the other 3 until we got telescopes, right? And so the question is, how would you construct a model for this? And the first successful model comes from one of the most interesting places in all of history, which is Alexandria, Egypt. 150 AD, you have Claudius Ptolemy putting down what became known as the doctrine of the perfect circle. So this is a model for the planetary motion. It is a circles upon circles model, which is one way to think about it. And notice I'm now starting to get framed here in terms of neural networks, is if this is my data, then I am learning a coordinate system in which to represent the dynamics. In this coordinate system, the dynamics are circles on circles. So when you think about a planet going around, it's on a circle, then it's on another circle, and then on another one. Okay? So that was this idea of the doctrine of the perfect circle. As far as we know, and maybe it will hold, it's the longest lasting theory in history that we have, like 1,500 years before it gets dethroned. Another way to think about it, who's taken Fourier transforms? This is the first version of a Fourier transform. You decompose that signal into a set of frequencies and harmonics. Okay? So there it is. So maybe it should be the Ptolemy transform, if we, because that's the model that really is there. This is only one model. And it would take about 1,500 years until the model gets dethroned to a second model. And this is the model that we commonly study in school, which is the heliocentric coordinate system, which is you just make a change of coordinates. Okay? Einstein already said we could do this. The change of coordinates is to say, when I transform this, I have this coordinate system here that we typically know about, which is sun at the center, planets going around, and the equations of motion now are F equals ma with the inverse square law of gravity. Both these models are perfectly valid. Both these models are equally accurate. So why do we think this one's right? Okay? And by the way, do you really think it's right? Because that's where you actually are in the galaxy. I don't think anybody's going to argue that the sun is the center of this galaxy, right? It's a local coordinate system that works well for our approximations that we have. Okay? And so, but there are two models that we can use, and the important thing is, how do we want to think about them? Well, there are very important ways we think about them today that really relate to how we want to think about machine learning as well. So specifically, I have two faces here. I have Kepler, I have Newton. So Kepler actually worked with this coordinate system, and what he did, he wrote down Kepler's laws. He knew that in fact the planets were going around in elliptical orbits. He wrote all this down 87 years before Newton had his Principia. Now, Newton comes along, he has F equals ma. What are the solutions to F equals ma? The ellipses that we already knew. So why is Newton more famous than Kepler, when all he did was reproduce his results? And I'll tell you it's this way. What do we buy when we have F equals ma? With F equals ma, and by the way, this is machine learning right here that we have to think about. In some sense, what Kepler represents, he is fitting the data with a model, ellipses. He's built an interpolation engine. But when you have F equals ma, you have something that's fundamentally different, which is extrapolation. With F equals ma, you can imagine the following. What would it take to launch somebody, put them around the moon, and bring them back? You have no data. Right? F equals ma allows you to make that projection. By the way, do we really believe it? Not really. This is why you send monkeys first into space. Right? Because if it doesn't hold up, the monkey dies, not somebody. Okay? But it held up, and it was like, oh, seems to work out there. Then you send somebody to the moon and back. So this is a really important thing. These physics engines are not just like, here's a different representation. A lot of machine learning talks about generalization. I hate that word. I'll tell you why I hate it. Because generalization is meaningless. Do you mean you're interpolating, or do you mean extrapolating? If anybody ever tells you their generalization error is good, it probably means that they were just interpolating. In other words, they collected data in this region, and they were testing it in this region. Extrapolation is, I learned something here, I went way over here. Well, I have no data. Okay? Just keep that in mind. If you're in engineering, that is your job. Often is to walk outside and build a new technology. Okay? It might not be the job of the computer scientist as much, right? Because if you're working in vision, speech, language, maybe you just want to be a good interpolator, right? That's what ChatGPT does. All right, so here's the architecture I'm going to propose for us. It's called Shred. Okay, so we're going to go shredding. I'm going to tell you how awesome this is. And what it is a shallow recurrent decoder. Okay, so it's a time pipe glued to a space pipe. So I'm going to take measurements of a system. Remember, this gets back to the sensor problem. I'm going to take 3 measurements, and I'm going to build this thing and train it to, from the time series analysis, map to the full state space. And this is a generalization of what's called separation of variables. I have a time and a space component. So separation of variables, I know you have an undergraduate PDE course here, right? Who's teaching it? Someone. Okay, you're teaching it, right? You have like 40 people in here. So I don't know if anybody's taken the class, but in the first day, right, you're going to do the following trick. I'm going to walk you through it. And by the way, I'll tell you what the following trick is. But one of the most important pieces of this is, instead of doing this architecture, what I showed you, which is we take the data, we learn in encoding and decoding, what we're going to do only is decode. And the reason we want to decode is because we don't have to then compute an inverse. If you compute an inverse of a matrix, it's a highly numerically unstable thing to do. don't do it. In fact, I know none of you use MATLAB anymore if you're below a certain age, but if you do it in MATLAB and you say inv A, it says, warning, don't do this. Okay? And MATLAB only says that if it kind of means it. This has been known since the 60s. When you do an autoencoder decoder, you are by constructing computing inverse pairs. And it makes your numerical algorithm, your deep learning algorithm, super stiff numerically. I do away with it completely, and you're going to see the results of this. I went from training models with an encoder decoder that took 9 months to hyperparameter tune to an afternoon. That's the difference. Okay? All right, so here's the motivation. Here is 20-year-old Nathan, okay, taking my first PDE course. Here's the first day of class. You start off with a PDE. Here it is. U dot equals LU. L is like some derivatives in space. So like the heat equation is the thing you might consider. In fact, that's what I did the first day of class. Wrote down the heat equation. And he said, how about we try a solution like this? I'll write my solution as a product of space and time functions. And then you find two ODEs. And since the prerequisites to the PDE course is ODEs, it's like, oh, ODEs, I solved that last quarter. So one of them's super easy, just an exponential, and the other one you solve. You know, it's a boundary value problem. And then you have your solution. That was day one of PDE class, 20-year-old. So anybody in here PDs? I don't know if you had first day like this, but that was my first day. Okay, all right. So first day of class, there you go. All right, now here's the thing. This is the solution. It's all possible solutions. There's one last step. And this came at the, let's say, the last third of the class. The last third of the class is, oh, look at this. We have this solution, but what are the A of n's? I don't know what those are. So to get a unique solution, you specify the initial conditions. So right at time 0, here's what the state of the system is. And when you do that, you can take inner products against this solution, and what you find is the unique solution. You determine all the A of n's. Okay? All right, there's day one of class, and then we build from there. But that's like a standard PDE theory treatment. There's one thing that we never talked about in that class, and that I haven't found in any of my textbooks, which is the following. There's a different way to solve this. And it's obvious when I show it to you that you can do this, which is instead of solving the initial boundary value problem, which, by the way, is completely a fabrication. In a real system, there's no way you know this full state of the system at one time. Right? Like you don't have, like normally you have sensors. Like you don't ever have the full state of the system pretty much. This is almost just fake kind of configuration. What you might have is a sensor. So we're going to do the sensor boundary value problem, which is instead of proposing that the solution at one time, the whole at one time know everything, I will assume that there's one location in space, let's call it my sensor location, that I have a series of measurements in time. And at each time point, that's a constraint on this system. And in fact, if I have n time measurements, I get an n by n system of equations for those coefficients. It's equivalent, except for it's much more realistic. I could put a sensor in my system, just measure some time points, and do this reconstruction. That's the sensor boundary value problem. This is what Shred is going to capitalize on. So first of all, there's no inversion, and it's very simple separation of variables arguments. Okay? All right, so we can solve that and move forward. So here's the architecture. We're now going to generalize it to solving not linear PDEs, but whatever spatial system I'm looking at, which is typically generically nonlinear. So this is work that started off with Jan Williams, who's a grad student with me. So here's my time pipe and my space pipe. Time and space. Product of two functions. That's what I started with, all right? Separation of variables. So I'm going to take my spatial fields. I'm going to take some sensor measurements, 3. This is, by the way, isotropic turbulence. It's a very difficult data set to make predictions on. Here's maybe what the sensors are doing, measuring. And I train now the time history to the current. So in other words, I'm going to map at this current time, what's the full state space? Well, I have a series of measurements before that. So I have a time history to the current point. I use all that information to help me do this inversion. That's the mapping. In fact, It works exceptionally well. I can do this mapping, and I can, in fact, reconstruct even this very isotropic turbulence case. And I'm relying on three very fundamental things. And one of them I haven't talked about yet. So one of them is separation of variables. One is that I'm not computing an inverse. But the third thing in there is relying on what's called Tauchin's embedding theorem. What Tauchin's embedding theorem is, if we were all coupled together in a dynamical system and all interacting, if you took a measurement of me and my time history, all of you were encoded in my time history because I'm coupled to you. And what Tauchin says is, if I have a high-dimensional state system, a time delay embedding of any one of the variables gives me a representation of the dynamics that's diffeomorphic to the truth. That's the theorem, what it says. Okay? And so essentially, those sensor locations, when I take a time history, give me something diffeomorphic to the full state space of that system, except since I have a training data set, it's no longer diffeomorphic, it's exact. Completely pin it to the actual solution it's supposed to be on. Okay? So those are the three underlying theoretical pieces of this. And I'm going to demonstrate this on some examples. Okay, so the first thing I'm going to do is now use these sensors to do what's called model reduction. So here's a data set we pulled off from a benchmark data set called the WELL. And this is 2D shallow water equations on a globe. Okay, so the idea is that this sort of modeling weather. Here's what we're going to do. We're going to take 3 measurements anywhere you want. Okay, so I spent 15 years working on optimized sensor placements. So when I tell you the following, so I'm about to cut down my own work. I don't do that anymore. You don't need to optimize your sensor placement. This doesn't care. As long as the location you're measuring is connected to the dynamics, agnostic to sensor placement. Put them wherever it's convenient for you. Okay? Those are 3 random locations. Here's what the sensor measurements tell you. Okay? I run this through my time pipe, and I decode back to the full state space. So I have to have a training data set to do this. But once I do this, I now have a nice representation of this. And by the way, the training of this, if this is a very high-dimensional system, it can be expensive, except for a lot of these have very low-dimensional spaces on which you're encoding. In fact, if you were to do a singular value decomposition of this data, you'd find it's sort of low rank. So we can change this around instead and say, we'll take the data that's very high-dimensional, and let's actually look for a low-dimensional subspace, and then train, same thing, but now train on its compressive representation. So now you can go to really large-scale problems. And large-scale, I mean really large scale. We've worked on algorithms, randomized SVD, so you can go to billion by billion matrices, meshes that are just enormous. You can do the SVD in like 80 seconds on HPC. You can even farm it out to Amazon if you want. It'll cost you about $10. And now what you have is a low-dimensional encoding of this, and now you train on that low-dimensional encoding. So now I can do the whole training pipeline on this laptop in minutes. Okay? And so that's exactly what we do here. And so now we can take this, and I'm just showing you the results here. So here it is. Here's with 3 sensors. This is what the truth is supposed to be. That's our reconstruction with 3 sensors. That's the error, the difference between them. Okay? And again, the data set comes from here. By the way, all this code you can download, you can do it yourself. Okay? Everything's open source, data, code, all of it. Here it is if I have a moving sensor. So by the way, if I can let the sensor move, and if I have let the sensor move, I can have a single sensor. Not 3, just 1, moving around. As long as I tell it where it is in time, where it's in time and space, then I can train this whole thing. With a single sensor, you can do the whole thing there. And that's the result from a moving sensor. I think you can you see it moving around there? You can see it down here, see it moving down there? It's on here. So anyway. You could also say, okay, well, Actually, I could train it. Actually, I apologize. I'm going to go back one slide here. Okay. So that was with there. Mobile sensor, here we go. Oh yeah, so this one here, now we can go to move, also, instead of doing an SVD and all that data set, the natural coordinate system, since you're on a globe, is spherical harmonics. I can just project all the data into spherical harmonics. That's a lower dimensional representation. And now I don't even have to do an SVD, and I can just train on a global basis. The nice thing about the spherical harmonics is it is a general basis for spherical behavior. So we always get worried when you train on your data that maybe you have things that are outside of your data set, right, that you can't extrapolate out. But this is a global basis that works across, even outside your training data set. Yeah?
Quick question. I see flashes in your reconstruction air. What is giving that sudden increase in the air?
That's a good question. You occasionally have spikes in the behavior, like if you have like extreme events in this behavior, you'll see it show up here. Those are very hard to capture with times, you know, basically. Yeah.
It's impressive.
Yeah, no, it happens. In fact, I think anytime you have sort of, let's call it extreme events, those are very difficult to capture in general with the time series. And so we don't capture those. Okay? By the way, we have this on neural data as well. So if you're interested. We can also do this parametrically. So you can say like, well, wait a minute. What if I have different parameter values? That was trained on one specific, but you can train across parameter values. For instance, maybe I'm varying, for instance here, the Reynolds number, the flow rate. So I just train across all of them. And in fact, what I would do is take all the data, SVD data all at once to create a joint low dimensional basis, train it, and now I can deploy it into a new parameter regime and reconstruct in this new parameter regime. Okay? Now, same thing's going to hold here as any place else. If I have parameter regimes here, let's say here's my domain and I've got some training data sets in this parameter regime, I'll do well in here. The minute I move way over there, you're not going to do well. Right? Neural nets are fantastic, but they are interpolators. Okay? You can't walk outside of your training data set easily. Okay. We went to higher, again, go to real video data. This is video. I don't even have the governing equations for this. I don't care. I can just simply train this thing. I can take, here are my measurement locations down here, downstream, and I take the video, I turn it into a black and white from an RGB, and then here's the reconstruction. And this here is if I walk outside of a new parametric window, a new parameter regime, and you can see I still do quite nicely in these videos. Normally people don't show videos like this. This is really hard to do with model reduction in general, and this thing just kind of gets it pretty easily. You can also then do this in the point of view of, from the parametric point of view, with geometry. So one of the places that neural nets and deep learning has not made much progress yet in is shape optimization. This is really hard because shape optimization is typically some kind of mesh you're on and you're trying to make geometry changes, and every time you change the geometry, where you're collecting data has changed. Not only that, it's not clear what your model's doing in this new regime, but here we're able to train across simple geometries so far. We have a pathway towards harder geometries where we're going to change the shape and optimize the shape for something like drag reduction. So we can actually do this very nicely with this. Here's these different Reynolds numbers. And when you do this, you can actually find yourself in a position to, let me run the video of the second one here. Oops. These videos down here should run. Okay, sorry. I think the video's not clicked in here. So here's the behavior of this, and if you were actually look at all these, this one here, I'll show you the error profile in a minute, but it allows you to actually optimize the shape function itself with this kind of architecture. And again, these are all laptop level computing. Nothing was done on a GPU. This is all like someone's laptop and doing it in minutes, okay? And we compared it against all these other architectures. Here's the error metrics that we get. By the way, not only do we drop the error way down, we have a smaller model, less training data, and our training time is below all of them. So you win on all the categories that you're trying to win on. Why are we winning? Because we actually used a very simple idea of separation of variables, and we didn't have any inverse. So it's kind of obvious why you would win after the fact. Okay? All right. So this is all setting up, hopefully, the ability to convince you that this thing actually works for not only mapping the sensors to the state space, but then to build very rapid reduced models in this space. But really, this has always been my goal for a long time. I call it GoPro physics. You film something, and you feed that camera feed into your computer and say, oh, here's the physics that you're seeing in this video. In other words, instead of you being the expert and trying to say, oh, I have to go back to all my textbooks. Oh, I'm looking at some flow physics. What are the equations of flows? I'm the expert. You just say, go in here. Let's do GoPro physics, which is have the computer itself learn the governing equations. And so this architecture, since I don't have inversion, I'm going to do one extra step then. Here's my time pipe, space pipe, same as before. But now, remember, when I built this time pipe, it was the latent space of this time pipe that was coming into the decoder. And what I'm going to do is simply say, how about I impose some kind of regularization on that latent space? And what kind of regularization do I want to impose? What I want to impose there is to say, have it give me a model that's interpretable. So what do I mean by an interpretable model? There's two versions of this that we can do. One is what's called SIND, the other is called DMD. And I'll talk about both of them. So all we're going to do is add pieces like this to our loss function. Now let me walk through what those pieces are doing. The first thing we might do is what's called sparse identification of nonlinear dynamics. This is called SIND. And what it is a method for inferring governing equations. So I give you time series data, and what this does is try to predict, okay, what is the PDE or ODE that gave me that data stream? Okay? And the way it works, it's just AX equal to B. I give you, for instance, some data X. So here's the idea. So here's the model system. But I give you the time series data X, Y, Z. I didn't tell you where it came from. What you know, it was from some dynamical system, X dot equals F of X. Well, I gave you X, so you can produce X dot. Okay? What's F of X? Well, you don't know. So instead of saying, well, I don't know what it is, but I know a lot of things it could be, so I built a library of candidate functions for F of X. Like, well, it could be this, this, this. Go to the library. Pick out some books. That's where your F of X's sit, right? Your knowledge. You're overeducated, every single one of you. So you just pick out a bunch of stuff that you know, you put it in there. And then what you say is, these are all the possible candidates, and then I do a regression. So that's AX equal to B. What X is the coefficient in front of these. And what we're going to assume here is that the sparse identification says, when we look at governing equations, typically, almost every governing equation we have is parsimonious. Doesn't have very many terms. Quantum mechanics has 3 terms. Maxwell's equations can fit on a t-shirt, right? Navier-Stokes, 3 or 4 terms. The philosophy here is that there's an underlying process that only needs a few terms. So when we do this AX equal to B, we promote sparsity, select as few of these as possible. So it's a sparse regression on AX equal to B. And we've shown that to be a very effective way of extracting PDEs and ODEs out of systems. By the way, if you want the package for this, you can pip install it. If you're bored with my talk right now, you can just open your laptop there and just pip install PySynD, boom, you'll be ready to go. Lots of examples in there. Or you could build a linear model. Let's call this dynamic mode decomposition. It's another architecture for doing this. Dynamic mode decomposition basically goes back to that linear PDE solve, which is this, I take snapshots of my data, and it's a regression directly to the solution form, which is exponentials. E to lambda t times some modes and some coefficients. That was my separation of variables solution for a linear PDE. So you just simply say, I believe that's the solution form, and to get to it, you do what's called optimized DMD, which Travis developed, and Dia then built a bagging optimize, which kind of made it more robust. Again, you want to use this technique, pip install PyDMD, and you're off to the races. But either one of these we can impose in the latent space, so let's do it. So we're going to go up here, we're going to impose this in the latent space, we're going to say, learn the dynamics for me. By the way, here's the model we're going to do. I'm going to take sea surface temperature data downloaded from NASA, 20-year period. We're going to throw it in there and say, what can you learn? The amazing thing is, this is what it learns. You can pinch the latent space all the way down to 3 dimensions, and it's a 3-dimensional linear ODE system. And here are the 3 modes, and by the way, it's glued to these 3 modes nonlinearly. So this is the Z1, Z2, and Z3. They're nonlinearly combined to actually have the outcome. This is remarkable. This is real data, right? And so here is our 100-week rollout where I write down the analytic solution to this data set. The other option you have available to you is global circulation models, which on HPC, right, is massive. Takes a very long time. And but you can see here, I have an analytic solution in the latent space. And it's not perfect. You lose some of the high frequency features. Neural networks actually act like bandpass filters, both in frequency and time. Here's another video. Real data, right? I love YouTube. Everybody love YouTube? Okay. I don't love the infinite scroll bar because I get caught up in it sometimes, right? And I just get lost. But, you know, whatever. Sometimes you find cool stuff, though, by infinite scrolls. And here's one of them. Flow around the cylinder, right? Somebody did this cool experiment. They put dye on here. Normally what we do is simulations of this, but it's a lot more impressive when you simply say, I'm going straight from video and I want to learn physics. This is the idea of the GoPro physics. Well, so here's what we did. We turned it into the original video in 2, from RGB to black and white, right? And then so that's the video. Here it is in black and white. That's the real data. And what we did is we had 200 frames to train on. So again, the data requirements are pretty low. 200 data frames. And now we're doing a projection 180 frames into the future. So this is the real data. This is the Cindy shred that we did, where we imposed Cindy model. Here's the model it learns. It's a 4x4 nonlinear ODE that has a fixed point and a limit cycle. So if I want to roll this very far into the future, I have a stable model to do so. And I've learned a new physics model for this system. This is a really well-studied problem. And here we've learned something new about it, which is this model here, which allows us to roll out. By the way, if you tend to roll out any of the other models, if I don't build a model here, I try to roll a GRU out, an LSTM, an RNN, a transformer, I roll it out into the future, it will blow up or go to 0. My prediction, if I just use any neural network time series modeling, will eventually fail. Here, I can roll this out as far as I want. That's if I want a nonlinear model. What if I want a linear model? Same thing here. Now, instead of 4-dimensional nonlinear model, it's a 6x6 linear model. There it is. Okay? So I can roll that thing out now, and I actually have an analytic solution for this. Again, learned straight from the video. Okay. What about a pendulum? Same thing. Here's a pendulum. Hey, since we're at a state school, and I'm from a state school, here's some fun things. I want you to notice the off-white walls, cinder blocks, with the off-white linoleum floor, with the off-white tile. So when you come and drill a hole in the wall, nobody cares. Because if anything, you've made everything look nicer, right? Okay, so we made it look nicer as a piece of art, but we just took video and said, can we learn physics? And in fact, you can pinch it down all the way to 2 dimensions, and that's your model that you learn. So first of all, check it out. You get your sine theta term. You have a damping term, but it's not theta dot. It's theta dot squared. You know, normally what we do is we always make an empirical model of damping, which is just proportional to velocity. That's what we teach in our physics class. It's not the data tells you. The data tells you that it's the velocity squared. You get small corrections to both. And sort of this is what this nonlinear pendulum is doing, at least with this joint in the wall and its damping. We compared this method to all the sort of competing video prediction techniques coming from computer science. So because we sort of have a lot of these physics principles built in, not only do we do better in accuracy, we train at a fraction of the cost, we train at a fraction of the amount of data, and our memory footprint of the model is a fraction of the size. You win in every single category. This is, I think, what it means to try to go after physics-informed machine learning. You should take everything you've learned in physics, every principle that seems to work well, and embed it in there. And what we embedded in there, right, was separation of variables, tokens embedding, no inversion. Because we knew all these things were good ideas, and it shows up here. It shows up in the sense it's like it beats all these things very nicely. Last example I want to show you is this, because this is a really hard problem. It's turbulence, isotropic turbulence. And what you're looking at here is we said, let's go and try to build a model for turbulence. Okay? And so at the top row, you're looking at, this is like a 600 frame rollout. Actually, if you roll it out a little less, we have a better result than this. This is an old result. We've improved it somewhat. But basically, if you roll this thing out, your model and the actual turbulence actually agree quite nicely. And what you end up with is in the latent space for isotropic turbulence, a 20 by 20 linear ODE system, which is kind of a remarkable thing to say about turbulence. The turbulence database from Johns Hopkins, the reason they built it is because it was so expensive to do these computations that there was a big effort by the community to build these things so that people wouldn't, because it's inaccessible to most of us to do these. They're there, and now we're saying, it's like, oh, look, in the latent space, I got a 20 by 20 linear model. And I can roll this out very nicely. That's the reduced model, but also I'm learning something about the nature of turbulence in this. Okay? So those are sort of highlight what the capabilities of this method are. So again, I think in sort of finishing this up, I wanted to say that the magic of this partly is being, if I'm critical of tech, tech has too much compute and too much money. Their solution is, oh, just bigger computers, more compute, more data. And I don't think they're thinking hard enough. For us in academics, for me, I have to think a lot harder because I don't have access to 1,000 GPUs. So I worked last year, I was in London, and I worked with DeepMind, and they have 1,000 GPUs standing at the ready. For anybody who's like, oh, yeah, I'm going to spin up a job. I mean, I can't even mention this, right? For me, I'm like, I got no GPUs, I got my laptop. Plus, my grad students know how to put stuff on GPUs. I don't. So if I can do it at laptop level, I'm so happy. And so in some sense, by thinking about all the physics principles, what this has allowed us to do is thinking about how we do this, we can come down to laptop level computing and beat a lot of the leading computer science techniques. And I think that's, and again, I'm going to point out that this is stuff that was 20-year-old Nathan. When I was 20-year-old, I learned this stuff, right? Separation of variables. So it's not like it's some sophisticated thing that I had to go do a postdoc and then in a very esoteric room with 3 people who understood what we were talking about. This is like what 20-year-old first day of class. That's what we're talking about. Okay? So if you want to learn more about it, I'm sorry, I'm going to be shameless here and put this up. We made an entire playlist of this. Now, the reason I put this up is for 2 reasons. First, I give an overview, but in here, we've built a PyShred package. We show implementation of it. We walk through the code. I've done this before at workshops now, where I've gone to the audience. I don't have time today because I have to go right after this. But I've always said to people, hey, you got a data set. Make some time with me. Bring your NP array with your complex spatial-temporal data. We'll sit down. We'll have it basically this shred architected within 1 hour. I am 8 for 8 on that. When people have actually taken me up for it. And by the way, the reason it took an hour, because I asked, you heard me say I want an NP array, but they was, oh, I got an HD5 file. So HD5 does not sound like NP, but fine, the first half hour is to take the NP, that HD5, turn it into NP array, and then 30 minutes later, we have it working. The code is there. You can download all of this. And even for the models there, we have a really little Colab notebook that you can just download and run. It has the sea surface temperature data, walks you through everything. So if you're interested in trying this, and this is laptop level computing, okay? So it's not this massive, go get some GPUs, then come talk to me. This is like, you can do it just like I can on my laptop. And here are the ideas it's relying on. 3 fundamental things, okay? And with that, I will stop. Thank you very much.
Thank you for a wonderful talk. Any questions? Really, really wonderful talk.
Thanks.
Thank you so much. Actually, I have learned PD when I was 20 years old. Okay. But there's one question I never get asked. Now I think you maybe have to ask this question. This assumption of the separation of variables. How do we know that's true for all of the PDEs?
Yeah, so great question. How do we know that's true? Well, it's interesting because even like the wave equation, which you're better off writing coordinates that are x plus ct, x minus ct. But if you have a basis expansion, you can still represent the wave equation in a Fourier basis, for instance. Okay? So in some sense, what the neural network is allowing you to do is by letting the latent space work in that decoding, it will just find the best way to represent whatever data you give it, whether it's waves. I mean, you've seen all the behaviors here, right? Model after model where you have moving features, turbulence, all of it, it just says, look, I will learn for you a latent representation of this and represent it. By the way, on that, even if you do numerics, for those of you who do numerics, spectral methods are built upon separation of variables. You just simply say, I'm going to project onto a basis with time evolution of the coefficients. That's exactly what this is in many ways. So if you want to think about this separation of variables idea, it's also like a spectral solver, but now it's learning spectral elements as it goes. One way to think about it. Yeah.
I have one question.
Yeah, go ahead.
Yeah.
Ask another one. And then
Okay. So the last piece of learning is the ODE, right?
Yeah.
In the latent space. I mean, that's kind of very intriguing, but it could be dangerous too in a sense, right? Because you're not really capturing the physics. It's kind of feeling. It's in a sense feeling the physics, right? But my question is, for example, how stable it is, meaning the same system, if I give you more data or different data, but in the same kind of dynamic systems. You try to fit it again. You may get a different set of ODEs. And how stable that is, you know, how do you interpret that kind of stabilities?
Yeah, maybe I can answer that with what we've already shown with Shred is you can build parametric models. So what we'd love to have here is this experiment with different flow rates, different densities, where if we encoded the parametric pieces, what we really want to learn, and this is what we're working on next, is, in fact, what we want is not this model, but instead of this being 0.98, we want it to be with mu and with beta. In other words, the model it should learn is with parametric dependencies directly. We actually think we've got progress on that, but that's exactly, then when you go to a new data set, it's like, it's the same model, but this data, those parameters are shifted, right? And so that's where we have found success, that even if you trained on a set of data, if you go to a new regime, it says, look, same model, I just have to shift the parameters. Now, if it's totally different physics, that's a different thing.
Thanks for really interesting talk. So my question about is the sensor location selection. We discussed it yesterday, but you sense any, let's say selecting any locations for the sensor point, right? But still, not very intuitively, because if the three locations are a bit correlated, then perhaps it's bad, or I would wanna say, select some orthogonal location or something like that.
Yeah, I would say it more like this. With high probability, random selection is going to work, right? So you can certainly get very unlucky, right? There's definitely the possibility of getting unlucky, but like if you do random selection, it's very much like the wording they use for compressive sensing, which is with high probability, it's all going to work. That doesn't guarantee it to work. Yeah.
Thank you.
Yeah.
More questions? Yes.
All right, so Jun basically stole my question, but I want to follow up on the stability thing. So what are the chances that you would get something if you ran this again where it wouldn't even be of that form, right? So here you have, 4 equations, three terms. What are the chances if you ran it on data set 2 from this that you would get something that's just a completely different form?
No, you'd always get, so this is interesting because normally when you train a neural net, the latent space every time you train it is significantly different. But when you penalize this latent space with that specific loss function, there is a global optima that all of it syncs to. In fact, we're going to put the update of this paper on the archive. The code's already available to GitHub. But one of the things we found that was sort of staggering is the loss landscape of this neural network here, right, this guy here, is globally convex. I only know one other paper, like Tom Goldstein at Maryland. He once did this regularization, and this paper made it into NeurIPS. It's got 2,500 citations from a few years ago, because he found this regularization that made this convex landscape, and you never see this, ever. And we don't know why that's the case, but we started looking at it, and the first time I saw it, I just about fell out of my chair, because it's like, it wasn't just convex, it was globally convex. So this thing is always going to the same solution every single time. And that's why we never have to have hyperparameter tune. So when I say I'm going to sit with you, and within half an hour of having your MP array, I'll have it working, the only reason I can say that is because I don't have to hyperparameter tune. Every single one of the examples I've shown here, we didn't really touch the parameters. Just ran it out of the box with the defaults. I didn't have to, because the global landscape just says, just, boom, I'll walk it downhill for you right into the solution. We still need to understand that, but it's a borderline miracle. So,
Yes.
Thank you so much for the session.
yeah.
Thank you so much for the session. I'm just having a question that which are those sensing technologies which are those sensing technologies like quantum sensors or biosensors or any IoT sensors which are expected to have significant impact on ML application in coming 5 years? Basically, which will be having.
Oh, what sensor technologies? Oh, that's a great question. So the question is, what sensor technologies are going to have the greatest impact? I wish I had a good answer. The fact is, it's sort of a marvel to me. Like, really, what people, I'll take neuroscience for an example. What people are able to do there now, it's mind-boggling, where they can put these neural pixels in and record from thousands upon thousands of neurons, but also like do whole brain imaging. Like, I mean, it's an astounding feat. So discipline specific, it really matters. In that discipline, they're just going to get, seems to me, get better and better measurement technologies. I don't know, like if you're measuring ocean flows or climate, really you just need good pressure, temperature gauges that you need. So it depends a little bit on what you're measuring. But I think the evolution of those sensors are going to power all of this. And I think the most important thing, if there's a take-home from here, is if you measure pressure somewhere in some kind of system, and you look at the time history, in that time history is encoded all the other fields it's coupled to. And I think that's partly what this story is about, is to say, like, you get a lot more information than you know in this thing, and if you have the training data to pin it, you now have the ability to measure things cheaply and construct very expensive things. So, yeah.
Okay, one more question. I was thinking about that. Basically, you were saying that when you want to measure the whole space, you can just do it with very few sensors, or maybe just one sensor. So I was thinking about the local behavior around the sensor. So for example, I have worked on sensors with air quality measurement, for example. So sometimes there is, for example, there is smoke burning around that small sensor. So you have only that sensor for the measurement, and overall the air quality is really good, but that sensor is measuring very bad air quality. So, like, how do you take into account the local aspects or the local without having measurements very different?
Yeah, I guess we haven't really done that. I mean, in some sense, there's a bunch of video data. Like, so first of all, there's a bunch of real data here. The data, the sensor is a camera, right? And where we've actually done real sensors, so if everybody loves Formula One, I love Formula One. I was at McLaren last year, the F1 team, and we were mapping pressure taps to PIV measurements. They're terrible measurements. Really bad signal to noise. And this is, by the way, when I knew Shred was awesome. Not just because it was on a Formula One car, but because it was terrible data. And I could take any 3 taps on that car. They didn't believe that, but so I did a bunch of experiments. See, it doesn't matter where you measure. Doesn't matter where you measure. Take any 3, and I will construct the PIV plane. And both datas were terrible, and it did within minutes, you got a great model. So somehow it seems to be very robust. Again, for further exploration, why that is, I think it's because of the convex landscape and no inversion. Those are my two, those are words, right? But really what you would want to do is put some math behind that, which we hope to do in time. But it seems, in other words, I guess the short answer to what you were asking is it seems to be very robust, even crappy sensors.
Okay, because of time constraints, we should stop the questions here, so let's thank